loading. And welcome. So we're going to do this next chapter on the sources of magnetic field. And we're going to talk about a number of things. We're going to talk about Boyer-Savart, which is a technique. We'll talk about forces between parallel currents and Ampere's law, which is another simplifying technique. And then we're going to talk about a thing called magnetic flux, which is analogous to electrostatic flux. And we'll talk about Gauss's law for magnetism, which is analogous to Gauss's law for electrostatics, but less interesting as it turns out. And then we'll talk about, very briefly, about this displacement current, which is a way of avoiding a problem. It's like it's a way of visualizing this work applied to capacitors to avoid a problem. So we'll get to those bits. Boyer-Savart is big. Parallel currents is big. And Ampere's law are big. That's where the meat of the stuff is. So let's talk about Boyer-Savart. Bit of derivation to begin with. We have a nice flexible piece of wire. We have a current flowing through it. We have a little bit of length in the direction of our current flow. Now, in this case, the current flow is causing a magnetic field. Okay, before we were talking about current flowing inside a magnetic field. So you've got to draw a line between the last chapter and this chapter. Last chapter, we had the current flowing inside a magnetic field. Now, effectively, we have a current flowing creating a magnetic field. So that's what we're about this time. So there's a fundamental difference between what we just did and what we're doing now. And so we have, we have a little bit of length of wire with a current flowing through it, and we have a point of interest. And I want to know what the little bit of magnetic field is caused by that little bit of current flow. Okay. So it's going to be this. And I pull it out of a hat. There's no proof to this. Consider a magnetic field dB, the little bit of magnetic field at a point P caused by current flowing through a length of element ds. The position vector relating the length element ds to the point P is r. So it's not actually on this. It's not actually on this diagram. That's r. There's my position vector. Basically, it goes from there to there. I didn't draw it along the line because I don't want to make my diagram too complicated. This is the unit vector in the direction of r, and this is the length of r. So there's three things going on there. That's a magnitude. That's a unit vector. There's my position vector. So, nomenclature matters, Under these circumstances, what is my little bit of magnetic field? My little bit of magnetic field is mu naught. That's the permeability, not the permittivity, the permeability of free space over 4 pi times the current times the little bit of length crossed with my r. And I don't justify that at all, over r squared. I don't justify it. It just comes out of a hat. It's one of these things. I'm sorry? It makes sense. Good. Pull it apart and, look at it from a dimensional point of view, visualize the cross product. Yes, and if this increases, does that increase, etc. Yes, good. That's a good solution. If you don't derive it, play with it, Okay, so mu naught is permitted free space. It's got this wacky number, 4 pi times 10 to the minus 7 Tesla meter per amp. And I don't expect you to know that. You can always leave things in terms of mu naught, and I prefer it, actually. If I take all the little bits, so there's another ds, and here's another ds, and here's another ds, and here's another ds, with a different unit vector and a different r vector and a different unit vector, a different r vector, and different angles in between, I can say that my total magnetic field is going to be the integral of this, which would equal, well, take out all the constant stuff. Mu naught is a constant, current's a constant, 4's a constant, pi's a constant. It's the integral of this cross product here over r squared. Okay, still not particularly nice. So what we're going to do about this? And what we're going to do about this is we're going to kind of simplify. Skip a slide. We're going to simplify. So what we're always going to do, I'm only going to ask you about the magnetic field at the center of a section of a circular current carrying wire. Could be the whole circle, could be half a circle, could be quarter of a circle, could be 7/16 of a circle, could be 5.5 circles. But I'm only going to ask you about the magnetic field at the middle of that path. Why? Because then R's constant, and well, there's a whole bunch of reasons. R's constant. My vector R is always at 90 degrees to my vector ds. My unit vector R hat is at 90 degrees to my vector ds, and so life gets so much simpler. So, it says a current carrying wire is bent into a complete circle. I got a complete circle. Use Boyer-Savat method as taught in class to show that B at the center of the circle is B equals mu naught I over 2R, where I is the current flowing through the wire and R is the radius of the circle. So this is another one of these cases where if you don't show me all the steps that I want, then you don't get the points for it. You got it. You can't just remember the answer because it's the process I'm after. And so the first thing you're going to do is you're going to state Boyer-Savat's law. And then you're going to turn around and say, well, look at this. R, the point from my ds to my point of interest is constant. That's kind of nice because that means I can take the R squared out of the integral. So let's do that. And then I say, well, now I'm looking at my integral, which is a cross product. And you know what? The ds is perpendicular to my R hat. And my diagram is not good. My R hat is actually there. Ignore that bit. My R hat is actually points from the wire to the direction, to the point of interest. That's interesting, okay? So it's still the same thing. ds is perpendicular to R hat. And the second thing is, of course, R hats are always equal to 1 because it's a unit vector. They've got a magnitude of 1. So when these guys, of course, are perpendicular, it becomes the integral of ds R hat. And R hat is equal to 1, so that becomes the integral of ds. Oh! The integral of ds is just equal to the length of the wire. That's kind of nice. So I say B is equal to mu naught I over 4 pi r squared times the integral of ds, which equals mu naught I over 4 pi r squared times, well, what is my length? Well, I know because I learned my equations at the beginning of physics 1 that the length of the circumference of a circle is 2 pi r. So, okay. So that means that this is going to be 2 pi r. Then cancel, cancel. The pi goes with the pi. One of the r's goes with that. 2 goes with that. So I end up with mu naught I over 2r. And then to complete this thing, in this case, r is not a variable. We actually have a value for r because it's an actual specific example. And the value for r is big R. Might seem like a small point, but it's putting in a constant value for a variable. So B is equal to mu naught I over 2R. And there's my answer. Now, you will not get prove this. I suppose I should do. Maybe I could do. But you would get what is the value. And so you'd substitute numbers in. You'd substitute the value in for R. You substitute the value in for I. You can leave mu naught alone. That's the methodology. Okay. So what are you going to face? Maybe it's going to be a third of a circle. Now, how would I tell you that? I could say it's a third of a circle. Or I could say it is 120 degrees. Forms a section of 120 degrees. Or forms an arc of 120 degrees. Yeah, so I can mess with that. I can clearly mess with the length. The radius, of course, that's just a number. The other thing I can do, which if you think about it, is I use the radius and I use the length. And they are linked. For a circle, my length equals 2 pi r. For a semicircle, the length is equal to a half 2 pi r. For a third of a circle, the length is equal to a third of 2 pi r. For 16/17 of a circle, the length is equal to 16/17 of 2 pi r. So I can mess with that, but once you see the pattern, it's no big deal. But the other thing I can do is when I'm giving you numbers, I have a choice. I can give you the value of r, and so you're substituting up here, or I can give you the value of L. Well, that's nice because this is the value of L. So if I give you the value for L, I've given you that bit already. But what I've not given you is that, the R. You do need the R. So if I give you the value of L, you've got to figure out what the value of R is that goes with that value of L. Does that make sense? So sometimes I'll give you the value of R and not mention L. Sometimes I'll give you the value of L and not mention R. Well, actually, can I do that? Yes. I could say a semicircle has a circumference or a length of 5 meters. Never mentioned the R, but you've got to figure it out. Okay, so there's 2 ways in. Okay, so watch out for that. And for me, they're not really different. It's just visualization and math. Not different. This says a current carrying wire is bent into a semicircle. Use Boyer-Sabat method as taught in class to determine the value of B at the center of the semicircle. Assume that the current flowing through the wire is 5 amps and that the radius of the semicircle is 2 meters. Can you do that for me, please? Let's put this on pause. So we're back, and so here's the layout of this. We basically wrote down Boyer-Sabat's law, and then we recognized that R was constant, so we were able to take that out of the integral, and then we recognized that ds was perpendicular to r hat, and r hat has a magnitude of 1, so we're able to take basically simplify our integral to being the length, and then we recognized that half a circle is half a circumference, which is half of 2 pi r, and then we're just rearranging and substituting in numbers. Something that was pointed out by one of the classes that if you look back at my old notes, and this is all down to me, I had r with an arrow on top rather than r hat, and it should be r hat. So that's a source of confusion. So please make sure you go back and change that. I've just not noticed that. All these times you just fly over it. I've not noticed it. That is r hat, not r with an arrow on top. They are very different things. R with an arrow on top is that guy, and r hat is that guy. And we're dealing with r hat on this. So, so there we have it. Okay. So watch out for that. I'm sorry about that. That's me. Okay. This next one kind of looks horrendous. It's not. It's basic. And the reason why I'm showing you it is actually because I just want you to see that, you know, hey, this is not such a big deal. It's basically the same problem, except we're not going to look at the point that's on the plane of the loop. We're going to look at a point that's along the line away from the plane of the loop. Okay, so then what would I want to do here? I'm going to say, well, okay, B. So here's my ds, and my r hat is in that direction, and there's my r. So it's kind of similar, but kind of somewhat different. And each one of these little DS's is going to create this little bit of field, and the thing that's not, this little guy here will create a little bit of field in that direction, and that guy there will create a little bit of field in that direction. So we're going to get a cone of these guys. You know, because each one creates a magnetic field at 90 degrees to the, yeah, that's the way that works. So we're going to be interesting on this. This is, I would not ask you this on a test, so we're just going to do this for the fun of it. I just want you to see that it looks horrendous, but it's not so bad when you look at it. So write down your Boyer-Savat's law. Boyer-Savat's law says that B is equal to mu naught I over 4 pi times the integral of, which way around was it? ds cross r hat over r squared. Okay, now let's step through it. Is r still constant?
Yes.
It is, isn't it? Because all those lengths, no matter where you are, it might be in a different direction, but they're all constant. So we can still say r is constant. So we're going to say, well, b is equal to mu naught I over 4 pi r squared times the integral of ds crossed with r hat. And the next thing I'm going to say is, well, hold on. Is my ds still perpendicular to r hat? There's my ds going along the top, and my r hat is going down there, and they are still at 90 degrees to each other, aren't they? Because of the symmetry. The ds is at the top, and my r hat is now there, but there's still 90 degrees to each other. This is my ds. So my ds is still perpendicular to my r hat, and also my r hat is still got a magnitude of 1. This is the same old, same old. So b is equal to mu naught I over 4 pi r squared times the integral of ds, because that's what all that does. And my integral of ds is equal to, mu naught I over 4 pi r squared. Now, if I add up all these guys, if I represent this as a circumference, is it still a circumference? Yes, because it's a complete circle. So it's still 2 pi r. Well, this is getting a bit boring, actually. Mu naught I over 4 pi r squared times 2 pi r. Now it gets a little bit interesting, because this r here is not the same as that r there. I kind of cheated a bit. I should have done that, because this r there is that, and that r there is that. Yep. Okay. So b is equal to mu naught I over 4 pi. This r squared. Oh, Pythagoras! It is constant, but it's given by r squared. Yeah, that's going to be times the square root of r squared plus x squared times 2 pi r. Okay, so I'm going to leave this. Let's try and get closer to here. So I'm going to simplify things. So mu naught I, my 2 pi and my 4 pi become just 1 over 2 like that. And then I have r squared plus x squared to the half, because it's square root.
Yeah, it should be just to the 1, because it's r squared. R is equal to big R squared plus big x squared, or to the power of a half.
It's a square root of...
It's the square root squared.
Yeah, but there's a plus there.
Oh, I see. So now, yes, you're perfectly right. So that's going to be... Shame on me. Did I make that mistake down there as well? Yeah, squared, isn't it? Because it's r squared. So then that squared, so that's going to be mu naught I over 2. And it's going to be r squared plus x squared. Yep. Still not there. And the reason why I'm not there is because, hold on. I got to take into account this component apart because these y components, or I'm drawing as the y components, those components are going to cancel, but the x components are going to add together. Okay? Okay, so that's what I've worked out. And I've got to figure out what that component is. And let's have a look. Oh, this, I'm going to call this B, and this is going to be B cosine that angle. Yep. If that's B, this is B cosine that angle. So I say, well, my B is equal to my B, which is mu naught I over 2 times R squared plus X squared. Now, hold on. Let me finish. Did I drop my R? I dropped my R, didn't I? Thank you. Let me finish, but thank you. So, okay, so then I got to do this component, and the component, well, cosine is adjacent over hypotenuse. Oh, adjacent over hypotenuse. There's an adjacent. Remember, this angle here is the same as that angle there because of geometry. So adjacent over hypotenuse is going to be R over the square root of R squared plus X squared. Now I see it. Mu naught I, those two R's make R squared over 2. R squared plus X squared to the 3 over 2. And there we have it. Now, I don't remember that. I don't practice that the night before. I kind of know the direction. I know, oh yeah, I got to take into account the component. Yeah, I'm going to be using Pythagoras. I remember that from, and that's what's hard the first time you see it. The first time you see it, you got to realize all those things. But once you've seen something like this, then you begin to recognize, oh yeah, I've got to use Pythagoras. And the reason why I really want to show you this is because I don't know what you felt, but the first time I saw this, my stomach turned. It was like, this is awful. And yet, with experience, what you realize is when you see something like an R squared plus an X squared or an A squared plus a B squared, especially, and it's like square root of it or some factor of square root of it, I'm thinking Pythagoras straight away. So that's kind of prompting me to look for Pythagoras in my question. So again, that's time on task. That's experience. It's not, and sort of my job is to try and encourage you to kind of like not be cornered by something that looks complicated, but to have the confidence that you're going to try and take it apart. You might not be successful the first time, but you won't be successful the 5th time if you never try. That's what I want you to say. It's tempting to just say, "Oh, to forget it, too hard, forget it. There's smaller fish to catch." But I want to encourage you to kind of try and take these things apart because you're building up your problem-solving skills on this. And they are certain patterns. It's not that the people who can do these things are just, Albert Einsteins. It's that they've trained themselves more or been trained more in it. So I just remember my first experience with algebra was trying to find the form of the answer that was in the back of the book and not getting that form. And sometimes when I think back, it was just my layout. It was as trivial as my layout was different. And I was too literal in my interpretation. If I had things in the wrong order, I'd fret about it. How did they know to put it in that order? The order makes no difference. So my reason for showing you this is to encourage you to just, things can look messy, but it's just physics in the end. They've got no more math skills than we have. It's just, more experience messing with stuff. Being prepared to tackle it. Cool. Let's have a look. We got 10 minutes. Yeah, we got 10 minutes, so we'll see how this goes. Next bit. Just an equation, really. We have, there's a bit of visualization. We have 2 current carrying wires. In this case, they're both going in the same direction. So I have the current flowing to the right and the current flowing to the right. And will there be a force? Well, yeah, because the bottom wire creates a magnetic field that the top wire sits in, and the top wire creates the magnetic field the bottom wire sits in. So they're both sitting in each other's magnetic field. And in fact, I can even show you this in some detail. If I draw the two wires side by side, so now I'm looking from down here. Now my perspective is down here. The currents are coming towards me. And then if I imagine, remember the corkscrew rule for current and magnetic fields is I use my thumb as the current direction and my fingers are the magnetic field. So this wire here with the current coming towards me creates a magnetic field that goes like that. I'm pointing my thumb out of the page and it's the right hand, so I'm curling my fingers around, and so my magnetic field goes downwards at this point. So over on my other wire, that other wire sees this downwards magnetic field. And then I say, well, hold on, the force on this equals IL cross B, and L is in the direction of my current flow, so the L is out of the page and my B is downwards, so my F is in that direction. And I can do the reverse thing on that side. What you realize is if the currents are flowing in the same direction, be they both towards you or both away from you, it's an attractive force. And if they're in opposite directions, it's a repulsive force. And you can get that from that terminology. You can remember it or you can figure it out. The magnitude, well, I've got to talk about the force per unit length. This is L. I'm sorry, it looks a bit like an I. This is L. Is going to be mu naught I1, I2 over 2 pi A. A is the separation between these two guys. L, let's get the diagram straight. L is that. And it makes sense. If I double my current in one of the wires, I have twice the magnetic field, so I expect twice the force. If I double the current in the other one, I expect the same thing. It's an over an inverse square relationship. An inverse relationship. As I double my distance, I only get a half the force per unit length. Okay, that's a little bit.
Why is that?
I don't have a good answer for that.
Oh, actually, no, because it's in 2 dimensions. Because it's if you treat the wires as if they're a one-dimensional object.
Okay.
So
Yeah, so it's not a three. Yeah, it's
that's
exactly.
the
Very
plane.
good.
It's a
Very
plane
good.
between the
It's
dot and
not three-dimensional. It's not spherically symmetric.
Yeah.
It's cylindrically symmetric.
Yeah.
Yes, excellent, excellent. Well done. So we say both wires carry current in the same direction, so the force is attractive. When the current in the flows in the opposite direction, the force is repulsive. By the way, you don't need to know this, but it's interesting. Time was when the current was defined by so many coulombs, 1 coulomb flowing per second down a piece of wire. That's very hard to reproduce. Involves wet chemistry, basically. There's institutions like the National Institute for Science and Technology in Gaithersburg, Maryland, big government lab. Employs an awful lot of science people. And part of their job is to make secondary standards. When you go to Publix and you buy your luncheon meat, that scale has been calibrated at the factory, and it will be calibrated against a SAN standard which has been provided by initially NIST. It might be through various distributors, but it all gets referenced back. And the NIST one finally goes back to the original one for the kilogram, I guess, and because we are a metric country. And they'll even have inspectors who come round and they will actually check to see the scale is working right. That's how you know you're not getting ripped off every time you go to a store. There's actually people who come round and check those things to make sure that people are honest. Well, they want as easy standards as possible, and so people said, measuring this current is a real pain. So when Eveready says this is 5 amp hours, how do we know that they're really measuring 5 amps or whatever? And the answer is, well, there's secondary standards for that, and it's a lot easier if you're not dealing with wet chemistry. So what they said was, we can use this attractive force between wires. So when the magnitude of the force per unit length between two long parallel wires that carry identical currents and are separated by 1 meter is 2 times 10 to the minus 7, this should be newtons per meter. The current in each wire is defined to be 1 amp. So it's a better way of defining an amp. It comes from the original definition. They didn't change the size of it. They just found a better way of showing it. And that happens a lot, actually.
Does it matter how long the parallel wires are?
Just long enough.
Long enough for the magnetic fields from...
So they can be assumed to be infinite, yeah.
Right, okay.
Yeah. So consider two parallel wires. One wire carries a current of 5 amps to the right. The second amp carries 4 amps to the left. Separated by 2 meters. Are the wires attracted towards or repel each other? So I'm going to draw it from the end. So that one is going away from me, and that one is coming towards me. So I do my corkscrew rule, and that one goes in that direction. There's my B. I'm sorry. Just messed up big time. That one's going in that direction. So the current is coming out of the page, and so my magnetic field is going in a counterclockwise direction, and so here it's going downwards. So now I do my right hand rule for vectors, and it's going to be I, L cross B. L is in the direction of current flow, and in that left hand wire it's into the page. So I point my fingers into the page and I curl my fingers down. So I end up with that, my F. Okay? Okay, you get that? So my L, if you like, use Q, V cross B. You know, your V is into the page because the current is into the page where that X is. So the current is into the page, so my velocity is into the page, and my magnetic field is downwards. So point into the page and then curl your fingers down, and your force points away. So I don't remember that, because I'm going to get it confused on a test. I'll just draw this diagram and figure it out. But that means it's repelled. Yeah. And then what is the magnitude of the force? So let's see if I can remember that. The force per unit length. Force per length. Force per length is mu naught I1 I2 over 2 pi a. It's like a circumference, not like a sphere. So that would be mu naught, and that would be 4 times 2 over 2 pi times a. That's 2 again. I'm sorry. 4 times 5 times 2. So that's going to be 20 over 4, 5 mu naught over pi, I think is the answer. 20 over 4 is 5 mu naught over I, and the units will be newtons per meter. And in a test, I'd want you to work out the pi, just so that we all do the same thing, but leave the mu naught. Occasionally, so this is the dilemma you get as a grader. Occasionally, somebody will mess up on multiplying by the pi, and it's tempting to just turn a blind eye to it, but if they keep messing up on stuff like that, they need to pay attention to it. So you want to smack their hand a little bit, but then sometimes they'll just leave the pi in which case then you don't even know if they messed up. So what do you do then? Question.
First per unit length, you mean that you should have put force per unit length right there in the question?
Yes. I can't ask you for the force unless I give you length. And this equation is the force per unit length, yeah. Just a bad question on my part.
So if you had given the length, you could ask force. If the question had length in it?
It would, I could, yeah. If this section, what's the force on this section of wire? I could do that. Okay. I want to just go back, because I skipped a page, so I want to talk about this. Is it just this one? Yeah. And this is like, it's a little bit out of place, I suppose. It's whenever you see things that are similar but different, put them down on the same page and compare and contrast them and just try and see how they go. So, okay, I have my electric field, and I remember this. It's Ke integral dq over r squared times r hat. And it's a constant times an integral, and this is certainly a constant times an integral, so that's similar. And rather than my little bit of charge, I have this, ds crossed with r hat. It's an r squared relationship, and in both cases. And well, this is length and that's length, so okay, yeah, I can I'm okay with that. Visualizing, if I pick a certain distance from my charge, it forms a sphere, spherical shell, and my electric field vectors are perpendicular to that shell. They follow radial paths. They diverge from a positive, yeah? They are, the magnetic field, the electric static field strength is proportional to 1 over r squared, because if I go twice as far away, I have something that's that's 4 times the area. This is interesting, because this is my wire, and I'm showing again the same distance from the wire, but now my magnetic fields are not radial, they are tangential. And so mathematically this is better to describe by what? A curl. Yeah, this is a curl. And bum, 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 bum. And this is where the bit that always gets me a little bit uncomfortable. It's still a 1 over r squared relationship. Because of that, but again, there's this r business up here, which is modifying it, okay? So compare and contrast, okay? How many of you have done divs, grads, and curls? Divergence, gradient, and the curl. How many of you have done that? Calc 3?
I mean, we're working on gradient now.
You're doing gradient now, okay. Yeah, okay. So you've touched on it, or you will touch on it. It makes, again, it's a tool that makes you more powerful. It's a better form of analysis. I got 5 minutes. I'm not going to go through this in 5 minutes, but I'm just going to give you the beginnings of it. Okay, so when I have a wire with a current flowing through it, I get these concentric rings of magnetic field, and depending on the direction of the current flow, then if it's coming out, then I have them flowing, in this direction. It doesn't matter the direction, but they're just flowing in the direction. I know as I go further away, my magnetic field strength falls. As with all things in physics and engineering, I want an equation. An equation has an equal sign. Equal sign says what's on the left is equal to what's on the right. I look for consistency. I'm looking for something to say constant. As I change one thing, I want it to be cancelled out by something else. And so the obvious thing that comes up is, oh, look at that. When we had Gauss's law for electrostatics, as the area of the sphere got bigger, so the electrostatic field strength got smaller, and they cancelled each other, the two effects. So I had a consistency. In this case, I'm not dealing with areas, I'm dealing with circumferences. And so the question is, as my radius increases, my circumference, my B gets less, but my circumference that the B sits on gets more. So is there a consistency? You might kind of, if you believe physics is simple, it's just it applies itself in many manifestations. You might say, oh, I'm suspicious, and sure enough there is a consistency here. What we find is, as you go further and further away from the wire, the magnetic field decreases, but the circumference of that circle you're on increases. And so the two effects cancel each other out. We say consider magnetic field around a long straight current carrying wire. As we move further away from the wire, B decreases, but the circumference of the circle increases. Is something conserved? And the answer is yeah. And so we end up with Ampere's law, which is, Ampere's law is the line integral of B dotted with ds is equal to a constant mu naught times I. And that again comes out of a hat. At this stage, we're pulling things out of a hat, a bit more than I like, but we're pulling things out of a hat. So, okay. And so next time, we're going to use this. So we'll just read through this. An infinite long current carrying wire follows the y positive axis using Ampere's law as shown in class. Show that B for this situation equals mu naught I over 2 pi r. And we start off by stating Ampere's law, and I'd like you to be able to state Ampere's law. You recognize, here's my ds, and here's my B, because it's created in the same, by the wire, they're both tangential, so B is parallel to ds. We recognize that because R is constant, B is constant on the loop. Notice the loop is my Ampere's loop. It's an imaginary loop. It happens in this case to coincide with a magnetic field line because I like that. It makes my math simpler. Because when B is parallel to ds, then what I can get is parallel means that my cosine theta goes to 1. B is constant, so the line integral of B dot ds goes to my integral of B times my integral of ds, which is my length, when you think about it, 2 pi r. It's the length of the loop. So then rearrange. And we'll come back and we'll talk more about this next time. Okay? So I'm going to stop here.